real-time interfacing, how to connect the microcontroller to the different peripherals such as ADC and DAC, digital to analog converter, and also we have seen an example, discussed a example of a temperature sensor, how to connect a temperature sensor to the microcontroller. That is a application, real-time application, the measurement of temperature. A transducer, how to connect to the 8051 microcontroller. LM34 and LM35, these are the transducers of the temperature sensors. We have seen how to connect LM34 and 35 to the 8051 microcontroller to measure the temperature. And we discussed a one of the important application of the 7-segment display. In that we have seen how to connect a 7-segment display to the microcontroller. The code we have discussed, the use of the 8255 PPI, programmable peripheral interface, which is used to connect to the microcontroller through the 7-segment. And the 7-segment, there are two types of the 7-segment displays: common cathode and common anode. Each segment is of diode, so these diodes are used to emit the light. These are the LEDs. So we have 7 LEDs arranged in a rectangle shape, and we have the 7 LEDs, and these LEDs consist of anode and cathode. If the cathodes are grouped together to the connected to the a 0 or a ground, and we have to give the high plus 5 volts or a 1 to the anode. Simply we are forward biasing the segment to generate the luminance, or it have to generate the optics, it have to glow. For that we are sending 1 for the common cathode. In a common anode, all the anodes are grouped together. R plus positive are connected to the plus 5 volts, and we have to give the low to the or 0 to the cathode to glow. Okay, that particular segment. So common anode and we have the common cathode. We have seen an example of the connection of active load logic, means common anode display where all the positives of the anode are grouped together and connected to the common terminal plus 5 volt or 1. Okay, and the remaining cathode that we have to provide with the 0 or low or connected to the ground. Okay, so active low logic, if you give the 0, then the segment will be low or segment will be illuminate. So that is a common anode. We are using that common anode in our interfacing example. And also we require the different ports of the 8255. We have the total 3 ports: port A, port B and port C. Again the ports is divided into 2 parts, or split into 2 parts. Okay, port C lower and port C upper. Please recall, in port SEM already I have discussed about the programmable peripheral interface, that is a PPI 8255. So the 8255 we are using to connect the 7-segment with the microcontroller. In between all the peripherals we require these 8255 to expand. What is a PPI? The 8255 is used to expand the input output lines. Okay, we required more input output lines, then we have to expand. And how to expand? And also we have to amplify the signal. Okay, for that we require the PPI, programmable peripheral interface. The interface, to give the interfacing between the microcontroller and peripherals. In between we require the 8255, please remember. Okay, so 7 segment display, how to generate the PDAEC 102, that example we have discussed in yesterday's class. Now today let us continue the remaining real world interface. We are discussing about the model 4 and model 5. So this already I have discussed about the EDC. This is the 8051 and this is the ADC, how to make the connection. And this is the DAC, digital to analog converter 0808. It is the internal structure, the use of the R2R ladder network. Okay, then this is the equation, very important equation. V by, this is the V by R, Ohm's law, and these are the weights, A1 by A2, A2 by 4, A3 by 8, A4 by 16, A5 by 32. These are the weights of the digital signal which has to be generated at the output. So based upon the digital weights, input is digital and output is analog. Based upon the weight of the input digital signal, we are generating some output current I naught, and this I naught again we are converting into voltage by multiplying the 2.5 volt, sorry, 2.5 k resistor. Okay, so that is a conversion to the input, conversion of the digital to the analog in form of current I naught and V naught. Okay, so V naught is the output voltage. Here we are getting the output voltage V out. Here you can see. So we have discussed about this temperature sensor. This is a flow chart, and this shows the use of the temperature sensor and the use of the ADC. We require the ADC because we are getting here the analog signals. So that we have to provide to the, we have to send to the 8051 microcontroller. So we have to convert this analog signal which is converted. Okay, here we have the a physical quantity, a temperature, pressure or any vibration. So LM35, LM34, this is the temperature sensor. Here we have the temperature. This temperature is a physical quantity converted into proportional current at the output. So here we have seen 10 millivolt for a 1 degree Fahrenheit temperature. Okay, in terms of Fahrenheit, so 1 Fahrenheit is equal to 1 Fahrenheit degree Celsius is degree temperature is equal to, it will generate 10 millivolts at the output. So 1 degree change of the Fahrenheit gives the 10 millivolt change at the output. So that is a transducer LM3435. So here we have the analog signal, a current and voltage here we are generating. Here we are generating the voltage. So we have the 8 channels, CH1 to CH8. So anyone we can use. If we have the 8 temperature sensor, then we require the 8. So here we have the analog. So this analog had to convert it to digital because the 8051 operate internal operation is based upon the only digital. So we have to convert it into digital form by using this ADC. And we have seen the example of the 7 segment and the code, the use of the PPI, the port A, port B, and their addresses. Okay, a table I have shown, please refer that table. Okay, now let us discuss the explain in detail with diagram the interfacing of keyboard with 8051 and also write an ALP. Also write an ALP, assembly language program, to interface keyboard with 8051. Okay, keyboard interface means we have the keyboard, they are arranged in rows and columns. They are arranged in terms of rows and columns. So these are the columns like this. So these are the 4 columns and we have the 4 rows. It is similar to our calculator, keyboard, or the keyboard what we are using in our PC connected with the keyboard. So like this, the keyboard is arranged in terms of rows and columns. So we have the 4 columns and 4 rows, and here, okay, this the interface between the column and row. If you press here, then this particular key will be activated. Okay, so we have to scan it. Okay, the microcontroller don't know which key is pressed. It would be better to have a scanner. The scanning is there, which is used to scan whether the current is generated or not generated. It is like a switch. Okay, a push pull switch. You might have seen the old mobiles which has the keyboard. So when you press that key, a current will be generated at the output of this particular row and column. This is the column 1, 2, 3, 4, row 1, 2, 3, 4. So it will be detected. Okay, the step is what? We have to scan. If this particular key is pressed, so when it is while it is pressed, it will generate some current at the output. So that current will be flow in a circuit. Okay, so like this it will be detected that in particular interface between the column and row a current is generated. Okay, so this belongs to some alphabet or number. Okay, let us assume this is A, this is B, C, D. Like this it is arranged, and also 1, 2, 3, 4. If it is pressed, it means it indicates that one is have to be displayed on the screen or one is detected. Okay, so this is the logic of the a keyboard interface. So keyboard interface, here we can see scanning and identifying the key, already I have told. So row is output, row is a output port and column is a input port. Row is a output port and column is a input port. So always, as I told, the row have to be as a output port and column is a input port. Please remember. So reading the input port means column will yield the ones for all the rows are grounded, and key is pressed, one of the column will have 0. So that combination, it is a 4 into 4 means in terms of binary, we are generating the combination of 1 0 1 1. Wherever we have the keys pressed, that will be 1 and remaining all are 0. Okay, so that is a scanning. So here I will give example D0 to D3. If it is pressed, there is no pressing between the D0 to D3, then it will be all high. You can see 1 1 1 active low. Okay, no press means all the signals generating from D0 to D3 will be 1 1 1 1. Okay, between the D0 to D3, if the D1 is pressed, then particular interface we are generating the active low. Please remember it is active low as I discussed in the 7th segment. Already I have discussed in the 7th segment. So we are using the active loop logic, means common anode. All anodes are grouped together and connected to the 1. And while we give the 0, then that particular segment will be glow, means we are making forward bias. Okay, keep in mind this is a diode and we have to make forward bias. Similar to here, in a keyboard we have the D0 to D3, they are arranged. If there is no key pressed, all are 1, 1, 1, 1, means active high. How to identify a particular key is pressed? So here you can see D0 to D3, they are arranged like a D0, this is a D1, this is a D2 and D3. Okay, if the D1 is pressed, that particular interface of the column to the row will be 0, active low. Okay, so this active low 0 will be identified. Whenever the 0 is identified, it means that D1, this position of the keyboard is pressed. Okay, so this is the logic of the scanning of the keyboard. So here you can see the circuit D0, D1, D2, D3 as I now only I have explained. So the circuit you can see here D0, D1, D2, D3. Please remember whenever we have these all four, there is no key pressed. No key is pressed. D0, D1, D2, D3. They are arranged like this. Here you can see this is the row, this is the column. This is a row and this is the D0 to D0, D1, D2, D3 are the columns. So like this. These are the columns. This is the column D0, this is the D1 column, this is the D2 column, this is the D3 column. At the same time, this is a D0 row, D1 row, D2 row, and D3 row. Okay, and here you can see the numbers 4, 5, 6, 7. Then you can see 8, 9. Then A, B, then C, D. Here you can see D, E, F. So these are the alphanumerical keyboard. Alphanumerical means we have the numbers as well as the alphabets. So all are connected together by 4.7K of the resistor to the VCC. Okay, so 4.7K of the resistor. These are the nothing but the current limiting resistor. Current, these are called as the current limiting resistor. Here you can see these are the switches. Here you can see these are the switches, a push pull button. If you want to detect these three, then this key has to be pressed here. Then it will be when it is pressed, then we are getting here 0. Okay, so D0 1, D1 1, D2 1, and D3 will be 0. Okay, so 0, 1, 1, 1. Whenever it is 1 means there is no key press. Here we are getting 1, here we are getting 1, here we are getting 1. Okay, whenever there is no key pressed. When the key is pressed at that interface here, we are generating 0. So 0, 1, 1 if you are getting at the output, it means that the 3 is the key related to third one. 3 will be, we have to activate this particular keyboard of the 3. So friends, remember this circuit, the rows and columns, and the use of the rows and columns, how they are arranged. These are the rows and these are the columns. Okay. Now this is the code assembly language program for a keyboard interface with the 8051. So already I have told, if you want to make P2, P1 and P2, okay, if you want to make P2 as a input port, you have to make FF, you have to put FF to the P2. Okay, so this is the FF to the P2. Then this is the K1, K2, and this is the over row 0, row 1, row 2. These program are used to check, scan, and also used to match. Okay, so remember this code, and this is the absolute call. These are used to generate the delay. Okay, 7.8 millisecond. How much time you press the key and how much time the current had to be generated at the output, decided by the delay. Okay, so this you have to remember. Here this is ASCII lookup table. So 0, 1, 2, these are in the ASCII. Okay, please remember, already I explained about the ASCII code. If you put anything between the two quotations, so this is the ASCII. So ASCII zeros equivalent hexadecimal will be converted. Okay, one's hexadecimal will be converted. 1, you can see 1 is between the two quotations. Okay, and 2 is also between the two quotations. Means these are the ASCII. Okay, for each row. Okay, we are discussing about only row, and columns are kept constant. We are getting the output from the column, and row, from the row we are getting the these input. Okay, so like this 0, 1, 2, 3, like this, these are arranged. I think you are getting my point. This is the K code 0, K code 1, K code 2, K code 2. This is the nothing but the equal, one of the assembler directive. Okay, next coming to the a very important concept called as a stepper motor interfacing. We have the many application of the stepper motor. A stepper motor is what? It will convert the electrical pulses into the mechanical movement. It is a motor. Okay, what is motor? Which converts the electrical signal into the mechanical. Okay, it is called a stepper, means the output is in form of step. It will not rotate continuously. Okay, it is not rotating continuously, but the rotation you can form, you will get in terms of steps. So many advantages of the stepper motor. You can use these stepper motors in robotics. Okay, disk drives, dot matrix printers. You can see in daily life. Okay, many applications of the stepper motor that translate the electrical pulses. What is stepper motor? Widely used device that translate electrical pulses into mechanical movement. Then it is called as a stepper motor. Okay, so these are the applications: disk drive, dot matrix, then position control. Stepper motor commonly used have a position control. What is the structure of the stepper motor? It is shown here. It is like this. Any motor consists of a rotor and a stator. So this is the stator A, this is the D, this is the B, this is the C. A, this is the B, this is the C, and these are D. These are the windings. Okay, these are the windings. We have the 4 stators. Here you can see the 4 stators. They are named as A, B, C, and D with the polarities N. Here you can see the N. These are the S. This is the S. And in between these stator, We have the shaft called as a rotor. This is the rotor. Okay. Because of the magnetic field here, when you apply electrical signal, the electrical signal causes the generation of the magnetic field in this winding because of the attraction and repulsion. Okay, repulsion and attraction. There is a jerk. You can see the movement of this rotor. Okay, so these are the stators, fixed one with the windings. To this winding we have to give the electrical, because of the electrical signal they are excited and magnetic field is generated in this. They are generating a magnetic field, and due to the magnetic field, this N and N, this is the rotor. Okay, this N and this N both are same, then it will be repelled. Okay, then again N. Okay, because of the positive and negative, it is in a sinusoidal. Whenever it is a positive, this is the N, this is the N, both are repelled. Okay, then it will comes to the next, 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 next. So like this in a clockwise direction or anti-clockwise direction, based upon the excitation provided to the stator. The movement of this rotor will be clockwise or anti-clockwise. Okay, and each step, okay, it have to complete based upon our requirement. It have to rotate for 360 degree, 180 degree or 90 degree or only 45 degree. So any angle of the rotation of this rotor we can have by using the coding and by using this excitation. Okay, based on this excitation, how we provide the excitation, the electrical pulses to this stator. Based on that, we can observe the rotation of this rotor. Okay, so here you can see one more figure, that is a second one. This is the north, this is the south. Again we have the A, B, C, D. Okay, so I already told because of the repulsion and attraction, there is a movement of this rotor. So stator winding configuration, how these A, B, C, D, the stator. Okay, these A, this is the B, C and D. How these windings are connected together. All the windings are grouped to a common. Okay, this is the common. Here you can see A and B. This is the A and this is the B. These A winding and B winding both are grouped, connected to the common. Here you can see the common. At the same time, C and D. This is the C and this is the D. These are the stators arranged in the horizontal position. A and B arranged in a vertical position. Okay, these are the vertical, these are the horizontal. So here you can see the C and D, both the stators C and D connected together and to the a common. Okay. So each step, let us assume we want 360-degree rotation. 360-degree rotation of the stepper motor. How much step it had to required to complete to have this 360-degree rotation. Step means the stepper motor operate in a stepwise, only step, there is no continuous movement here, you can observe. How much is this step angle? Okay, how much will be the a step angle? So this is the stepper motor. Okay, so this is the center point. How much angle it will require to complete the entire 360-degree rotation, either in clockwise or either in anti-clockwise. This is the anti-clockwise and this is the clockwise direction. If you give the opposite direction excitation, then it will rotate in anti-clockwise. Okay, based upon the excitation If you give the excitation like this, then starting from A, then D, then B, then C, then it will rotate in clockwise direction. If you reverse the excitation, means A, then C, then B, then D, then it will rotate in anti-clockwise rotation, anti-clockwise the rotor. Okay, based upon how you give the excitation to these stators. Okay, so based upon that you can observe the rotations. Here we are discussing about the 360. Okay, for the 360 degree. Okay, we want to find number of rotations, number of steps. Okay, so what have to do? 360 degree we want the full rotation in clockwise direction. Each step is how much? Each step is how much we have the angle. So that is called a step angle. Okay, this is the step angle. Each step like this, how many steps it have to complete to have this 360? Okay, that we are calculating. How to calculate? We want 360 degree and 50 steps to complete this 360. Okay, this is the 1, then 2, then 3, then 4, 5, 6, 7, 8, like this. 50 steps we required to complete the 360, and each step is of how much? So that is given by nearly 7.8 degree. Okay, 7.8 degree. Each step is of 7.8 degree. Okay, so this is a simple logic of finding the 7.2 is a step angle. So here you can see the two columns step angle. If the step angle is of 0.72, then how much steps required to complete the 360 degree? Getting? So 360 divided by 50, you will get 0.72. Okay, if the step angle is of 1.8, then how much steps are required to complete the 360? So 200, 360 by 200, you will get 1.8. So similar to there, you can see if the 24, here you can see 48, it will be nearly 7.5. So each step angle is of 7.5 degree. There are two methods of the interfacing of the stepper motor with the microcontroller. Okay, remember, if the question is like this, the interfacing of 8051 to the stepper motor using ULN, here you can see ULN 2003. ULN, there are two methods to interface the stepper motor with the 8051 microcontroller using ULN 2003. This is the first method, and second one is using the PPI, programmable peripheral interface 8255. So based on the question you have to write the answer. Okay friends, there are two methods to interface a stepper motor with the 8051 microcontroller. This is the 8051 microcontroller. Okay, so this figure you can see use of the ULN 2003, the first method. Okay, there you can observe this is a stepper motor. As I told, we have the two windings. This here you can see here, these are the two windings. These are the stator, these are the stator, and this is the rotor. Okay, these are the stators, the windings where we have the windings called the stator, and in between we have the rotor. So here you can see the stators. These are the stator windings here, and this is the rotor of the stepper motor connected together. Here you can see are connected to the plus 5 volt, plus 5 volt, and second one is the use of the 8255. So this figure shows, you can take it the figure in a landscape. So this is the stepper motor, this is the ULN 2003, this is the driver. Okay, the why we require the driver? The current which is generated here by the microcontroller is in a very less in a strength, very weak in strength. So the current which is generated here is very weak in strength. We require the current to drive these stators. For that we require this driver. This is the one of the driver. Okay, ULN 2003 is a driver, and this driver is used to amplify the current and to drive these stators. Okay, and based upon the electrical pulses received from this microcontroller, there is a action, the rotation of the stepper motor. Okay, so this is the driver. Use of the driver ULN 2003. Okay, and these are the current limiting resistor of the 4.7 K. Okay, and port 1 we are using the port 1.0, port 1.1, port 1.2, port 1.3. These are the port 1's 4 pins of the 8051. This is used to control the stepper motor operation, whether it have to rotate clockwise, anti-clockwise, 360 degree, 180 degree, 90 degree. So these all are controlled by the coding program which we burn here. Okay, which we burn here. So based on the microcontroller's program which is present in this microcontroller, based upon that the ULN generates the electrical pulses, and these electrical pulses are sent to the stator, and based upon the stator excitation it will rotate. This is the rotor. Okay, so this is the code. Okay, here you can see these are the addresses of the port A, port B and port C of the 8255 PPI. So this is the delay 7.8 millisecond. How fast? Okay, how fast it have to rotate will be decided by the delay program here. We can make fast and we can make slow. So that is decided by this delay code. Okay, nearly 7.8 millisecond is the delay. Okay, here you can see the count 100. Okay, so 100 means here you can see nearly 72 means step angle of nearly 5, nearly 6.5. Okay, if you put here the count 100, so that much of 360 divided by 100, so that means that is a step angle. With that step angle the stepper motor is rotating. And BB, here you can see the BB, EE, DD. Okay, here you can see the DD, then here you can see the EE, here you can see the BB. So these are used to set the excitation of the stator, whether it have to rotate in clockwise or anti-clockwise. Clockwise and anti-clockwise is based upon this sequence. Okay, here you can see the sequence BB, then here we can see the EE, then here we can see the DD. So this decides the sequence of the excitation. So based on this, okay, if you put the DD here means the excitation will be in reverse direction, anti-clockwise movement. If the excitation is like this, BB, EE, then the excitation will be in a clockwise direction. So clockwise and anti-clockwise based on this sequence how you put in a code. Okay, if you reverse this sequence, then it will be in the anti-clockwise. If you put in like this, then it will be in a clockwise direction. So LCD, which is similar to the 7-segment display. So instead of LCD, we are using the liquid crystal display LCD. It is a chemical composition. So like this, refer this figure. This is one of the liquid crystal display LCD. Okay, so go through this LCD. Then this is the model 5 interfacing through the 8255, the use of the very important PPI called as a 8255 programmable peripheral interface. So 8255, what are the features? So it is a 40-pin IC. Fourth semester also we have discussed about this PPI. I have discussed 8255, very important. It consists of 3 ports. They are named as a port A, port B, port C. Okay, and individual port we can program. The port A we can program as a input or output. B also we can program as a input or output by using read and write control signals. So this is the port A, 8-bit. So they are named as a port A 0 to port A 7. Port B, this is the port B. Port B 0 to port B PB7. Port B 0 to port B 7. So this is the 8-bit. Okay. Then we have the read bar, write bar. This we can program as an input or output by controlling the read and write. Write means input, read means output. So these are read bar means these are the active low signals. Okay, active low signals. Bar, it will be activated when you give the 0. Okay, so these are called the active low control signals. These are used to control the ports as an input or output. Here you can see a table. This is very important table. Chip select bar A0. This is the A0 and A1. So these are used to control which port had to be selected. Port A, port B, port C, and control register 8255 and not selected. So here you can see chip select 0, 0, 0. Then port A will be selected 0, 0, 1. Port B will be selected 0, 1, 0. Port C will be selected. Okay. Then if you put 0, 1, 1, then control word register will be selected. Okay friends. So this is the truth table of the 8255. How to select the ports, port A, port B, port C. This is the 8255A. Here you can see input. Okay. These are the inputs PA0 to PA7. Okay. This is the read bar, pin number 5. CS bar, pin number, read bar at pin number 5. CS bar, pin number 6. Ground 7. A1, A0. Okay. So this is 8255. Here you can see port A. This is the port B. This is the port C. Both are bidirectional. D0 to D7. Okay, D0 to D7. This is a read bar, write bar, A0, A1 and CS bar. A0, A1, CS bar. This is a A0, this is a A1. You have to make it change here, A1. Okay, so A0, A1, CS bar. These three are used to select the ports. Port A, port B, port C. Which port has to be selected? Okay, if you put 0, 1, 1, the CS bar is 0 means if you give here ground and 1 1 then it will be control word register CR. Okay, so this is the table and this is the how the 8255 has the different pins. So this is the D0 to D7. This is also the bidirectional. So we have the different modes of the operation: mode 0, mode 1, mode 2, then BSR, bit set reset mode. So remember this is the control word register. See, this is the control word register of the 8255. 8 bit D0, D1, D2, D3, D4, D5, D6, D7. So here always you have to put 1. Okay, so when you put here 1, so input output mode will be selected here. If you put 0 here, then it is a BSR mode. So BSR mode is very rarely used. BSR mode is very rarely used. It is not used. Okay. So D7, if you want to operate the port A, here you can see the port A. This is the port C, and this is the port B, and this is the port C. If you want to operate this port as an input and output, you have to put here always 1. It would be 1. Always it would be 1 here. Okay friends, like IE register, interrupt enable register. To enable that interrupt enable, you have to put always 1. So like this D7 here, always put 1. Whenever it is 1, then only all the ports have to be programmed as a input and output ports. So here you can see D0, D1. D0 is a port C. If you put here 1, then it is an input. If you put 0, then it is an output. Port C will be operated as a input or output by making 1 and 0. If you here put 1, then it is a port C will be operated as an input. If you put 0 here, then it will be operated as an output. Port C is lower. This is the lower bit. Okay. As I told, port C splitted into two nibbles. Port C lower and port C upper. So this is the port C lower. So lower PC0 to PC3. Okay. If you want output, then you have to put here 0. So similarly D1 port B. This is the D1 is for port B. 1, the port B will be activated as an input. If you put 0, then it will be operating as a port B will be operating as a output. And D2 is a mode selection, 0 mode and mode 1. If you put 0, it will be operating in a mode 0. If you put 1, it will operate in a mode 1. So this is a port C upper. Okay, PC4 to PC7. Again, it will put 1 here, it will be port C upper will be operating as an input. 0, then it will be port C upper will be operating as an output. So D4 is for port A. 1 input, 0 output. This is the port A. 5 and 6, 0 0 mode 0, 0 1 mode 1, 1x mode 2. There are 4 modes. There are 3 modes of the operation. So we can select any mode of operation 0 0, 0 1, 1x by putting 1 zeros at D5 and D6. Okay, and this is a D7 already I told, very important. Okay, so this is about the 8255. In next class, let us discuss the 8255 connection to the 8255 connection to the 8051 microcontroller and some examples. This is regarding the model 5. Okay, we are discussing about the model 5. Okay, any doubts are there? Friends, any doubts?
No, sir.
So let us conclude here and you can go for the next class. I want to stop here. Okay, any doubts you can ask, otherwise I will stop. Okay, thank you.